you to another week and another interesting statistical topic. Of course, I said something the other time. Statistics is more or less like a story. A story that goes on and on and on. Okay, so today we're basically going to start what I call parametric bootstrapping. Before I get started, I also want to remind you that the first assignment of the semester has already been uploaded. So I will advise you check the canvas for assignment 1 detail. Okay, so the other time we started bootstrapping. And of course, I sincerely want to appreciate those who actually provided feedback. Of course, I get some feedback from some of you, and I'm actually going to address that a little bit. Okay, so before I address the feedback, I think I'm going to show you what we actually want to cover today on the outline. Before I go into parametric bootstrapping, I think I'm basically going to revise with you what we've done on the non-parametric bootstrapping. Then I go to parametric bootstrapping, then you're going to see some examples. And I will advise that you pay attention. The moment you pay attention and you focus on the board, and if you have if you need clarification, of course I need you to direct your question to me. Yeah, go ahead. Not on canvas? That's so strange. Give me 1 second. I think I will have to tell my, do you want to check now? Don't know why you keep on like, do you want to check whether it's, I call it week 3 lecture 1. Oh, okay. Thank you so much. So I apologize for that. I think I'm gonna. Okay, so let me first talk about those who actually ask question about how bootstrapping work. Let me tell you, if you talk about business, somebody asked a question. That's an interesting question. The person said, how can one actually improve on, on our findings if we're not getting new information? Like, I'm only working with sample and I'm only, providing the general versions, several versions of the sample, but the fact that there is no new information that shouldn't, have effect in a way. That's an interesting question. But this is my response. If I don't want to go by statistical bootstrapping, when you talk about bootstrapping in general, you are talking about an entrepreneur who starts a business with little capital, okay? An entrepreneur who starts business with little capital, and this entrepreneur, okay, this entrepreneur does not rely on any money outside investments, okay? It does not, okay, rely, okay, it does not rely on money outside investments. He only focus on the little capital, but at the end of the day, that very business expand. Don't you think that has happened before? Somebody starting with little capital and the money, without relying on any money outside their investment, he or she was focused and the business was booming. Maybe he started with $5,000 and now, the total money on board is $1 million. That's a bootstrapping. Now, let me tell you this. On a real life situation, we are supposed to go back into the population to take more data. More data actually translate to more information. But I told you the other time, we're limited by budget and we don't want to conduct what I call a repeated samples of experiment because that is going to take a lot of resources. And that is the essence of taking sample in the first place. But let me now generalize this, that the only way the bootstrap is basically going to work, whether you are doing non-parametric bootstrapping or you're doing parametric bootstrapping, the only way it's going to work, your original sample that you choose from the population has to be a good representative of the population. I'm going to say that again. Don't forget, you only work with original sample and you are providing several versions of that. What I'm trying to say is that if the original sample that you choose from the population is a very good representative, you got to choose a sample in a way from the population in a way that that very sample you choose is a very good representative of the population. Otherwise, if that original sample is not a very good representative from the population, the bootstrapping effort is not going to work, no matter what, because you are only bootstrapping something that does not really represent the population. Now, reason for bootstrapping is what I stated here. You don't just bootstrap. Number one, I got small sample sizes. And not only that, this small sample size with unknown population distribution. You don't have the idea of the probability distribution. Okay. Then number two, the assumptions of normality does not hold. In statistical analysis, we pay more attention to assumptions of normality because when the assumptions of normality hold, it will be very easy for us to conduct statistical inference. For simplicity, okay? So very, very easy for us to call. It's not as if it's not as if we can conduct statistical inference when the assumptions of normality fail. We can still do that, but only that would, the approach that we're going to use will be complicated. For simplicity, the moment the assumptions of normality hold, we can easily, conduct statistical inference. And that's why we normally, focus more on that assumptions of normality. Now, another reason is skew data. When you're working with environmental data, you're working with some data, they may be skewed. How are you going to know? When you look at the histogram, when you look at the normal QQ plot, you'll be able to know whether the distribution of data is skewed or not. Okay? Then another, what if we are working with a non-linear combination? In statistical analysis, we have linear models, we have non-linear models. The linear models are very, very easy to undertake compared to non-linear model. The idea of bootstrapping is actually also going to work in a non-linear relationship. Now, what about location statistic other than the mean? It is not all the time that the focus is going to be on the mean. We could focus on median. We could focus on proportion. We could focus on difference. We could focus on ratio. We could focus on some other stuff. Okay, and focusing on some other statistic, the idea of normal distribution may not work. And that's why we have to go bootstrapping. Okay, now I want to have a review on non-parametric bootstrapping. Now, the idea behind the non-parametric. I wanted to pay attention to the word non-parametric in statistical analysis. When I say parametric, I'm actually having assumption on the probability distribution of my data set. That is parametric. But when I say non-parametric, the non-parametric is trying to say I don't care about the distribution of the data set. Now, there's something I'm going to walk you through today. I'm going to walk you through some example on non-parametric. I'm also going to walk you through an example on parametric, and I want you to see the difference between the non-parametric and the parametric. Let me tell you, when you go online, you're basically going to see some information, and I want you to know it is not all information that you see online that are true. You know why? You know, when somebody was defining parametric, he said, oh, when I'm working with probability distribution, I'm actually talking about parametric. That's a lie. And I'm going to tell you, you're going to see now. Now, let me tell you this. Do you know I may be working with a parametric distribution and I'm still doing non-parametric bootstrapping? How? I'm going to tell you. You know, every probability distribution has parameter. I'm going to say this again. Every probability distribution has parameter. If I'm talking about norma, of course, norma has parameter, mean and variance. If I'm talking about binomial distribution has parameter, N and P. You know, if I'm talking about Poisson distribution has parameter, lambda. You know, every statistical distribution has parameter. Now, let me now tell you this. If parameters are known, I'm going to say that again. If all parameters in a distribution are known and I'm bootstrapping from that distribution, I'm doing non-parametric. You know why? Because the parameters are known. But if one of the parameters, if it is not all parameters in a particular distribution that are known, if at least one is unknown, then I'm going to be going parametric. Do you see the difference now? I can still be working on a probability distribution and I'm still doing non-parametric. And I may be working with a probability distribution. I'm doing parametric. Now, what distinguishes between doing non-parametric and a parametric with a probability distribution depends on whether the parameter is unknown or known. Does that make sense to everyone? Is there anyone who is actually struggling with the way I talk? If you're not getting what I've been saying, I need you to signify. Is there anyone? Don't forget you pay for the service. Okay? So you can challenge me. It's your money. Okay, I'm gonna take you there now. Let's now see. Do you know what I'm doing here? Can somebody tell me? Oh, x1 less than minus arrow norm. Arrow norm, okay, if I want to simulate from a normal distribution, okay, you know, there's a distribution called normal distribution, and you know, a random variable x followed normal with parameter mu and sigma squared. You know, we have f of x equal 1 over square root of 2 pi sigma squared exponential this x minus mu over sigma or squared. X lie between negative infinity and infinity. This is a normal distribution. We got two parameters in a normal distribution. You can see the mean and the variance. Okay, now if I want to simulate from a normal distribution in R, I'm actually going to use R norm. Now I want you to look at the board. Now, look at the board. Now, look at what I'm projecting now. The parameters are already given. Do you know what that guy is telling me? Okay, let me first start with setting seed. You know, in this class, anytime I give assignment on bootstrapping, particularly where you are simulating, you need to set a seed. Why do we need to set a seed? because of the reproducibility, so that we can simulate the same set of data. If you don't set a seed, the data set you're going to simulate will be different from mine. Don't forget, we're simulating at random. And anytime you want to set a seed in this class, right? Set.seed 4051. That is the name of our course, right? That will enable us to have access to the same data. Now, I want to simulate. I want to simulate from a normal distribution. Oh, the first one, 50, means I want to simulate 50 observations from normal distribution with what? The mean of 2 and the variance of 0.25. What happened here? The parameters already known. Take a look at that. If I want to do bootstrapping here, I'm not going to do parametric bootstrapping. What kind of bootstrapping am I going to do? Non-parametric, because the parameters are already decided. Any question? Now this here, then I'm just going to go by the code. The X1 will actually give me the original sample of 50. Look at that. That X1 will give me original sample of 50. I'm simulating my data set from normal distribution with a mean of 2 and a standard deviation of 0.25. And the second one, B1, what am I trying to say? Oh, generate how many? 5,000, right? 5,000. That means I'm actually going to have 50, 50, 50 in how many ways? In 5,000 ways. How do I get that? I got the 5,000, of 50 from original observation 50, X1. And what am I computing? What am I interested in? I'm interested in mean. I'm interested in the mean. And at the end of the day, I do the bool.ci is the confidence interval, and I indicate different types of the confidence interval that we can have: the normal, the basic, and the percentile. And in the end, oh my God, look at my result. Is there anyone who want to ask question? I've succeeded in simulating from a normal distribution whose parameters are known, and I've succeeded in obtaining the confidence interval for the mean. Any question? This is a non-parametric, not parametric. Any question? Yeah, go ahead. Oh, that's a very good question. You know, I told you the other time where we have different kind of confidence interval. The normal one, for instance, when I construct the histogram and it is normal, I can decide to use the normal and the basic. But the moment it is skewed, the moment the histogram here is skewed, then I can't trust the normal and the basic. Then I'm going to go with percentile. Does that make sense? That's a very good question. Okay, so what I've done here, this is non-parametric. Okay, take a look at this guy. What am I doing again? Is it non-parametric or parametric? Can somebody tell me on this question? The second one, is it parametric or non? That I'm going to do. Yeah, what is that? Is it parametric or non-parametric? That I want to do now. Take look at the board. I have x2 less than minus arrow poise. Now, when you see arrow poise, that's a code to generate from Poisson distribution. Has anybody heard about Poisson distribution? Poisson distribution. You know, x follow Poisson with parameter lambda if f of x equal exponential raised power lambda raised power x over x factorial, s start from 0, 1, 2 to infinity. This is a Poisson distribution. We have different probability distribution in statistics, just like the same way you have state of Minnesota, state of Illinois, state of Mississippi. Don't forget, each of those states, they have their own laws. We also have different probability distribution in statistics. Now, this is what we call Poisson distribution. We use Poisson distribution to model count data. We use it to model count data. Okay, now take a look at this now. So, and if I want to simulate from a Poisson distribution using R, I'm going to write x less x equal r poise. R poise. That is why you're saying R poise. Now, here, the first value that you see is the number of sample that I want to simulate. The second one is the value of the lambda. Okay, lambda 10. So it means lambda equal to 10. The parameter in a Poisson distribution is lambda. Now, what do you think I want to do here? Is this parametric or non-parametric? Which one? Can somebody tell me? What do I want to do here? Yeah, non-parametric. Why? Because the parameter is already decided. When the parameter is decided, you see doing non-parametric. This is non-parametric. Okay, now you said a seed x2 less than minus arrow points 210 means simulate 200 data points with lambda equal to 10 from Poisson distribution. That's what it's telling you. And after doing that, then we are interested in the mean, generate 5,000. So it means you're going to have 200 data, 200, right? Data point in how many ways? In 5,000 ways. And each of those 200, you're going to find the mean. This is a mean, mu high. Okay? Then we get the confidence interval. Any question? That's super easy. This is another example of non-parametric. How is this different from the one we did before? The one we did before we already have our data, but now we're getting our data from a distribution whose parameters already decided. When the parameters are already decided, I'm still doing non-parametric. Now, I want to go to the next one. Like I said, we have so many probability distribution in statistics. There's another probability distribution called gamma distribution. You know, the gamma distribution is very useful in environmental study. Okay, very useful in survival analysis. Okay, X follow gamma with parameter. S follow gamma with parameter alpha and beta. You know, we have f of x equal x raised to power alpha minus 1 exponential raised to power minus x over that, b raised to power that, this raised to power that, x greater than 0. This is a PDF of a gamma distribution. Okay, this is a PDF of a gamma distribution. These are the parameters of a gamma distribution, alpha and beta, right? Now, if I want to simulate from gamma in R, I'm basically going to use, look at that. So R gamma. For normal, R norm. For Poisson, R poise. Look at that. For gamma, R gamma. Now, if you take a look at this, you basically going to see here, they say sample from gamma 5,1. Oh, 5,1, then the parameters are already decided. It means alpha equal to 5, beta equal to 1. Then what you're still going to do here is also going to be a non-parametric bootstrap, because the parameters are already decided. And don't forget, you are interested in mean. So right here now, you are generating, you said the first line produce 1,000 by 30 matrix of independent gamma variates, and each that row follow gamma 5,1. This is the code. Take a look at that. That is the code. In the end, you get the mean, you get the histogram, which is suggesting normal. Now, everything that we've been doing, you can now see what I just showed you now. We can also do bootstrapping from distribution. But if all the parameters of the distributions are known, you are still doing non-parametric bootstrapping. Now, let's go to the summary. Remember, the point of using a bootstrap is to estimate how the statistic of one natural sample of size n will vary because of random sampling. Of course, you know, from sample to sample, Okay, when you go into population several times, you expect the statistic to vary, right? And so almost all the variation among the bootstrap distribution for a statistic is due to the selection of the original sample. I told you the other time, the variation that you observe was due to the way you select the original sample. The original sample has to be a good representative of the population for your bootstrapping to work. Now, larger sample sizes perform better than the smaller sample size. Even though you are choosing the original sample, the larger original sample, okay, we actually perform better than the smaller one. That's what we mean. Okay, now I want to go into parametric bootstrapping now. Let us now see how parametric bootstrapping, how it is different from non-parametric. Now, when I say parametric bootstrapping, we're actually going to be focused in, we believe the data set that we have follow a particular distribution. And not only that, it is not all parameters of that distribution that is known. One of them is unknown. Okay, now what is the procedure? Let's look at the procedure. I said, why the non-parametric bootstrap is distribution free? You see, is distribution free? You may be wondering, oh, distribution free. Why are we simulating from from some distribution the other time, and we call that non-parametric, and we said that is distribution free? Of course, a probability distribution is not a problem anymore if parameters are decided. What makes a probability distribution to be complicated is when parameter is unknown. But the moment parameters is known, you don't have any problem at all. Okay, and we said the parametric bootstrap is based on the distribution, f of theta. Now take a look at that f of theta. The theta here is the parameter that is unknown. We don't know it. Okay, now what is the procedure? We're also going to use data from the original sample to estimate the parameter. Look at that. The parameter is unknown. The data set available, we're going to use it to estimate that parameter. Do we do that under the non-parametric? No, we didn't do that. We didn't do that under the non-parametric. Now, after estimating that parameter, you know what we're going to do? We're going to get a theta curve, right? When you estimate, then you now plug in that back into the distribution. Initially, what do you have? You got f of theta, right? Where the parameter is unknown. Now you estimate that parameter from the given information. And after you're done, you now plug in whatever you get into the distribution. See that? You do that. And after that, you now generate so many samples now, because when you estimate that, it means you have now decided, you have now computed the unknowns. You have estimated the unknowns parameter. Then you plug in back into the distribution. The moment you plug in back into the distribution, oh my God, where are you now? You are back at a non-parametric way of doing something. Okay, so when you do that, you generate 5,000 from that. Then you compute your statistic as we normally do. But in the end, the difference here is the statistic that you compute, you're actually going to subtract. That's your estimate from each of those statistics to get your data, to get your data. Okay, I'm going to demonstrate that to you. Then you can use that to compute your confidence interval. Okay, now let's get started. Let's see how the parametric work. Now I'm actually starting this example with correlation. Now I need you to understand this now. I want to do correlation, right? I want to do correlation. And don't forget, if I want to talk about correlation will come from, I'm looking at the relationship between X and Y. Oh my God, correlation is parametric because correlation depends on the means. When you look at the formula for correlation, okay, you're going to see mean, as in mean of x bar and y bar. Okay, correlation depends on the means. And those means, they have to follow normal distribution, which is parametric. Now, take a look at this now. I want to look at the correlation between LSAT and GPA, right? If I found the correlation, I got it 0.77637745. The value that I got here, don't forget, this is going into population once. That value is only reliable if the assumptions of normality hold. The correlation value that you always get is only reliable if the assumption of normality hold. If the assumptions of normality does not hold, then you cannot use this guy. Otherwise, you have to use different, or there are other types of correlation that we use, or you do bootstrapping. Now, this is a scatter plot. Okay. Now, the next thing we're going to do now is this. I said something the other time. We have, since we're working with X and Y, then the belief is going to be X has to follow normal distribution. Y has to follow normal distribution. Don't forget, when X followed normal, Y followed normal. That was the reason why we're talking about the mean, why we're calculating the mean of X, the mean of Y. Right? Now, the assumption now is we have a normal distribution, but we don't know the mean. If I want to go by the idea of parametric bootstrap, I will need to, for us, estimate the parameter mean. Don't forget, one of the parameters of a normal distribution is mean, like this guy. You know, when X follow normal, we'll have this and this. Now, this is unknown. Now, this can be known. If this is known, let's say this is known, and this is unknown, the interest is on this. We're still going to use a parametric. Now, look at what I'm doing now. How do I estimate? By idea of parametric is, okay, you know what you're going to do? You need to estimate the parameter. Don't forget, I needed to come back here. Okay, the theta is unknown. The theta in this case is mean. What do? We estimate that, right? Oh, the mean is unknown. How am I going to estimate the mean? Of course, I'm going to do the sample mean. Of course, I'm going to do this, guys. Look at that mean. I need the mean of this variable and the mean of that variable, right? That is the way to get the meaning out, right? And after getting the mean, now, if you look at this question, we want to do correlation, right? And there are two parameters in the normal distribution. Our assumption is that the two of them are unknown. The two of them. This is unknown. This is also unknown. Now, since the two of them are unknown, they need to be estimated. Now, it means in what I'm trying to do now, this guy here, the theta here is a vector. Why is he a vector? There are two parameters that are unknown. Don't forget, in this example of correlation, I'm talking about normal distribution. The normal distribution now has two unknown parameters. And what am I going to do? I need to estimate them. Now, in estimating them, I'm actually going to find the mean of each. And I'm also going to get the variance covariance. Look at that. The mean of that is this. Then the sigma is COV in R, mean covariance. You know, when I say covariance, what do I mean by that? Take a look at this. You know, this is going to be the variance of X, the variance of Y, then the covariance of XY, the covariance of ys. This is what we mean by that sigma. The sigma here, because I'm talking about two variables. If I'm talking about one variable, I'm only going to have variance. But how many variables am I talking about? Because I'm dealing with a correlation. I'm talking about two variables. I'm going to have a 2 by 2 matrix that we're actually going to call variance, covariance matrix, where the diagonal elements will be variance of x, the variance of y. Then these are the covariances. Any question? That is exactly what I'm doing on the board. Take a look at that. This is a code. Then I got this guy now. What have we done now? We have succeeded in estimating the means and the variance covariance. What do you think I'm actually going to do? After doing this, I'm now going to assume these values for the missing parameters in normal distribution. Then what do you think I'm going to do now? I'm going to simulate from them. Because the only way you can simulate from a distribution is when you already know the parameters. If you don't know the parameters, you can't simulate from that. And the parametric bootstrapping is only going to help us how we can figure out those parameters before they can now be used to, to simulate. Now take a look at what I want to do now. I'm going to load a library mask. I need that package. Then the 5,000 numbers. Then take a look at this. What am I trying to say now? Oh, I need 15 observation, right? Then mean sigma. What is my mean? Mean is what I've already computed here. What is my sigma? Sigma is a variance covariance matrix. Look at that. Now we are ready to do a simulation now. Do you know that after you have estimated your unknown parameters, whatever you're going to be doing now will be non-parametric procedure? Look at that. You are back at a non-parametric procedure. The parametric aspect, do you know the parametric aspect? The parametric aspect is you figuring out the unknown parameter. Now, this is a code now, right? Then I'm going to get my results. Okay. I do the bootstrapping. Oh, the bootstrapping that I am having now. What is it showing? This is skewed, right? That is skewed, right? Now, in this situation now, since this guy is skewed, okay, I'm actually going to use the percentile confidence interval here because it is skewed. Now, what if I want to, and you remember the other time when I was doing correlation with non-parametric, this is what we did. You know, we did it before. In the last class, we did something like this. This is the non-parametric aspect. The parametric aspect is what I just did. The only difference between the parametric and the non-parametric is that in the parametric, the parameters of the distributions have not been decided, and you now need to estimate those parameters. The moment you get the values of the parameters, you're now going to plug them into the distribution. Then you're now going to simulate your data from there. Then you're going to follow with the same process you've been doing under the non-parametric. I want to go into another example now. I'm still under parametric, but this time around, I want you to take a look at this distribution. Data from binomial 15 theta. Oh my God, 15 comma theta. That means I'm going to use a parametric here because this is the way binomial is written. You know, we use binomial in statistics to model outcome that is dichotomous. Outcome that have two possible nature. Now I'm going to say X follows binom distribution with parameter N and P. Okay, N and P. And this very P is the theta, okay, is the theta. So the f of x in binomial is n combination s, p raised to power x, 1 minus p raised to power n minus x, s start from 0, 1, 2 to n. This is a probability mass function of a binomial distribution. Now, merely looking at this, 15 comma theta means the size is 15, n is 15, but the theta is unknown. But let me tell you, the theta that is unknown is the same thing as p. What is p? This very p is the probability of success. P represent probability of success. Don't forget, using the binomial distribution is how you record success or failure. And P is the probability of success. And definitely that P will lies between 0 and 1. Even though we don't know the value for now, but the value is going to be between 0 and 1. Now, this is going to be a parametric bootstrap because one of the parameter is undecided. Now, what am I going to do? You're given data set. Look at that. X, 3, 5, 7, 9, 11, 13. You know, I told you in a binomial distribution, if X represents the number of successes, you can have a 0 success, 1, 2, and so on like that. So you are given that. And don't forget, you've been given the size to be 15. Okay? Now, if you don't want to do your simulation, your n is going to be the length of X, 1, 2, 3, 4. When you take a look at that, it's going to be 6. Now, I now need theta. How do I estimate theta in binomial? I want you to take a look at this now. When I have this distribution, based on what you've done before, okay, in binomial distribution, expected value of X is NP. Expected value of X is NP, theoretically, and expected value of S is mean, using the method of moment, right? Which is equal to NP. So if I now want to obtain my P, what am I going to do? P will be X bar over N. It means if I want to estimate my theta cap, if I want to estimate theta cap in binomial, it's going to be X bar divided by N. That is a formula here. You see, X bar, mean of X, divided by binom size. Binom size is N, given here to be 15. That N is this guy, the numbers of time you try, right? And the X is the number of successes you recorded, right? Now, that is why I have this guy. Now, the moment I got this, I'm now going to bootstrap. How many, I have 5,000, okay? Then, following this code right here, okay? You basically, going to have, in the end, I got is 0. The confidence level is 0.46 or 667 to 0.66. This is what I got. I told you the other time that your P is going to lie between 0 and 1. Now, this is the code. If I were you, what I just wanted to pay attention to, anytime they mention binomial distribution and you want to do the parametric bootstrapping, follow this code. Follow that code. You're basically going to be fine. Okay. This is an exercise for you if you want to try it out. What happened here? You've been given a size of 8, right? And you don't know theta, right? Follow the same code and you have been given what? The data. You can try that. Now, I normally award an extra credit if you try this and you are comfortable sharing that with me, right? Then you can, if you get it right, you're basically going to have an extra credit. When you answer my question correctly in class, you have an extra credit of 1 point. Or when I give an exercise like this, and I say, okay, I'll try it, and you send it to me through my email, you're also going to have an extra credit. You can be accumulating your extra credit point, okay? And Who knows, at the end of the semester, you're going to advise me on how you want to spend your extra credit. It could go towards assignment, it could go toward the midterm, it could go toward the final exam. So it's your extra credit. You can keep on accumulating that. I want to give you another distribution now, right? We want to bootstrap from exponential distribution. There's so many kind of distribution in statistics. But in simulating from exponential distribution, now x follows exponential distribution with parameter theta if f of x equal exponential raised to power theta minus theta x greater than 0. This is an exponential distribution. Okay, so the parameter is theta. So in this question, the theta is unknown, but you are given data. Okay, and the theta here is 1 over x bar. Okay, it's 1 over x bar. Your theta, the parameter here is 1 over x bar. We've worked out the MLE, the formula. Of course, in exam, I'm actually going to give you all this, like, okay, the estimator, for each of the, how to find the parameter, estimate parameter in each of the distribution. And that's why you are seeing 1 over x bar here. Look at that. Lambda, at times we use lambda. If they want to use theta, you can say lambda. That's no problem. Now, lambda is 1 over the mean of observation. Don't forget, these are your observations. You get the mean using that, then you get that. And after that, you do the bootstrapping. Okay, this is the first bootstrap, but if you go by 5,000 bootstrap that we always do, okay, if you go by 5,000 bootstrap we always do, then finally, if you follow what we've been doing, you're going to get the histogram, and finally, you're going to have the confidence interval. It's the same approach. Now, the takeaway from today's class is you can be working with distribution and you are doing non-parametric bootstrap, provided all parameters are decided in the distribution. But if at least one of the parameter is not decided, you're going to do a parametric bootstrap. And the moment you estimate, only that you need a formula. You need a formula to estimate. That formula will be given to you in exam. I'm going to suggest that to you. Okay? And after estimating that, you're going to plug in into the distribution. Then you now simulate. Then you continue in the process, in the conventional non-parametric process. Now, finally, let's look at the summary. The non-parametric bootstrap technique is very powerful tool for constructing confidence interval for a wide variety of parameter and scenario. Let me tell you, in statistical analysis, we use non-parametric bootstrap a lot, because with the non-parametric bootstrap, it means we already have our data set and we don't rely on any distribution, even though distribution is given, the parameters are already decided. And in fact, non-parametric technique was the go-to method among practicing statisticians when everything else failed and you run out of options. The parametric bootstrap technique requires you to select an underlying distribution, and this comes with issues and may not be straightforward. It was not straightforward. I need to first estimate parameter. I need a knowledge of mathematics to be able to do something, and at the end, they were able to get the result. Is there any question before I go today? Any question? Is there any question? Now, you know what I need from you today? This is the 3rd week of my lecture. I need you to send me an email message. I want to hear from you. What is your understanding up to this moment? What is your understanding of my class? Rate your understanding of my class from 0 to 100%. If it is less than 100%, tell me what you are struggling with. The greatest sin in the whole world is when one deceives oneself. If somebody deceived me I'm going to report the person to somebody, but if I deceive myself, who am I going to report myself to? And that is the reason why you know yourself better than anybody else. Do not hide your feelings. I want to hear from you. Okay, make sure you stay safe and have a very beautiful day. Bye for now, everyone. Yep. Okay. Yeah, go ahead.